Hello friends, in this video we are going to solve an important Fourier transform problem related to the frequency domain behavior of LTI systems. In this question, an LTI system with impulse response h of t is given and we are asked to find the output of the system for a given input x of t. For this type of problem, we never work in the time domain because it is very difficult and time consuming. Instead, we solve the problem in the frequency domain using the Fourier transform. To do this, we need to review a few key points. The output an LTI system with impulse response h of t and input x of t is equal to the convolution of the input with the impulse response. If we move this relation to the frequency domain, the Fourier transform of x of t becomes x of j omega, the Fourier transform of h of t becomes h of j omega, and the Fourier transform of y of t becomes y of j omega. When two signals are convolved in the time domain, they are multiplied in the frequency domain. This property, which converts convolution into multiplication, makes solving this problem much easier in the frequency domain. We also call h of j omega the frequency response of the system, and it plays a very important role in the solving this problem. The second point is the Fourier transform of sine of omega t divided by t, which we derived in previous videos, is a rectangular pulse in the frequency domain. This pulse exists from minus omega to the plus omega with an amplitude of 1. The third point is the Fourier transform of cosine of omega 0 t is equal to p delta omega minus omega 0 plus p delta omega plus omega 0. In the frequency domain, this corresponds to two impulses, one at frequency omega 0 and one at frequency minus omega 0, each with amplitude p. Similarly, the Fourier transform of sine of omega 0 t is equal to p divided by j times delta of omega minus omega 0 minus p divided by j times delta of omega plus omega 0. So in the frequency domain, this signal also consists of two impulses, one at omega 0 with amplitude p divided by j and one at minus omega 0 with amplitude minus p divided by j. The fourth point is the time shift property of the Fourier transform. If the Fourier transform of xt is xj omega, then the Fourier transform of xt minus t0 is e to the power of minus j omega t0 multiplied by x j omega. These were the key concepts we needed. Now let's move on to the solving the problem. General solution approach. First, we find the Fourier transform of the input. Then we find the Fourier response or h of j omega. Next, we multiply these two together to obtain y of j omega. Finally, we take the inverse Fourier transform of y of j omega to get y of t. The input signal consists of two parts. The first part is 2 times cosine of 3pt. Using the first point, its Fourier transform consists of two impulses at frequency 3p and minus 3p, each with amplitude 2p. And the second part is 5 times sine of 14pt. Its Fourier transform also consists of two impulses, one at 14p with amplitude 5p divided by j, and one at minus 14p with amplitude minus 5p divided by j. Now let's find the frequency response of the system. First, we write the Fourier transform of sine of 7pt divided by pt. According to the second point, this is a rectangular pulse from minus 7p to plus 7p with amplitude 1. However, if you look at the impulse response, sine of 7pt is shifted by 1 unit in time. So here t0 equal 1, and based on the time shift property, we must multiply by e to the power of minus j omega. In order to obtain h of j omega. And then j omega is equal this pulse multiplied by e to the power of minus j omega. According to the first point, y of j omega is equal to x of j omega multiplied by h of j omega. When we multiply this together, the frequency band from minus 7p to plus 7p remains, along with the factor e to the power of minus j omega.
if we look at the impulses, the components at 3p and minus 3p lie inside this band, so multiplying them by 1 leaves them unchanged. However, the components at 14p and minus 14p lie outside this band, so they are multiplied by 0 and removed. As a result, y of j omega consists of two impulses. One at 3p with amplitude 2p and one at minus 3p with amplitude 2p, both multiplied by e to the power of minus j omega. Now we take the inverse Fourier transform to obtain y of t. Using the known properties, the output signal becomes 2 times cosine of 3p times t minus 1. In conclusion, we can say that in the frequency domain, this LTI system behaves like a filter. It passes signals that lie within its frequency band and blocks signals that lie outside of it. If you found this video helpful, make sure to check out the other videos on this channel, where we solve practice problems in signal and systems.